Now we can substitute in for our normal force. If we go back up here and look at our force equations, go back up here, our normal force will be equal to our gravitational force of the first object, the gravitational force of the object on the table. So we'll have mu kinetic times Fg1 minus Fg2 divided by negative m2 minus m1. And that's our A. So let's substitute our givens. So this was 0.1 times the gravitational force on the 2 kilogram block would be 2 times 10 minus the gravitational force on the 10 kilogram block would be 10 times 10 divided by negative 10 minus 2 will give us our acceleration. So substituting in our coefficient of friction, the masses, the acceleration due to gravity, and solving, we get 8.2 meters per second squared is the acceleration. Now, earlier, the tension force we had solved for way up here, the tension force is equal to m1a plus the force of friction. So we can take that equation and we're going to substitute our acceleration back into it, and we will find the tension force. So the force of tension would be equal to 2 times our 8.2 plus our force of kinetic friction, which was the coefficient of friction times the weight force, the normal force, which was the weight force, 2 times 10. This gives us a force of 18.3 newtons. 18.3 newtons. Now, the most common mistake for a two-body problem is neglecting the direction of the net force. So this is a very important step here, to include the direction of the net force. This negative sign is probably the most missed negative sign ever. This you get lucky because it's positive, so it doesn't mathematically affect that because unlabeled is assumed positive. But missing this right here because of the net direction of the force will cause a mistake here.